Calculus course, lecture number 14. In this video, we will be studying linear approximation and differentials. So what's linear approximation? Is basically a very important tool in derivative application to estimate values like square root of x and sine of 25 degrees, or if you're finding uh, complicated values. It's a very important tool in approximation. So first, what we're going to do is we're going to start off with an f of x curve, right? F of x and a tangent curve, right? And build a theory from there. So we basically starting from the beginning. This is like foundation knowledge. Now, assume that you have a curve which is f of x, right? And you have a tangent line. Remember, we can find the equation of that tangent line to that curve at a particular point. So let's just say I have a curve like that, a little bit more steeper, right? And I'm going to draw a tangent line somewhere around near that point there. So let me just change the color of this line here. Okay. So the green curve is the original function. And let's put a point here and call it a and f of a, okay? And this is the tangent function. Equation of the tangent line, the black curve is the equation of the tangent line, or we call it a linearization function. Why we call it a linearization? Because it's a linear function. How come? Why is it a linear function at this point? Because it's a straight line. A and, if I take a point over here like 2 and become, y value become f of 2. So I'm taking a general point A and f of A, okay? And this is the green function is basically my f of x function, right? Now, we want to find the equation of the tangent line here, right? To find the equation of the tangent line to this curve, we say, remember, we need to find the slope. So m is equal to f prime x. F prime x gives us the slope function. But if we substitute the value of a inside f prime x, we will get f of a. And we have a point which is a and f of a. So what I am doing here is I'm trying to find the equation of this tangent line. We have done it before, I'm just revising this. If I find the equation of this tangent line here, it's a linear function or linearization. We will say y minus y1 is equal to m into x minus x1. So there's my x1, which is a, and that's my y1, which is f of a. Now, y minus, what's y1? It is f of a. My m, the value of m is f prime a, which is a slope, into x minus x1, x minus a. So now if I'm solving for the equation of the tangent line here, let's just put yt to represent equation of the tangent line. We say yt, the equation of the tangent line is f of a, I'm taking this f of a across, plus f prime a into x minus a. Okay, and this you can clearly see is a linear function. So we call this the linearization. It's a function in x, okay? F of a and f prime a are values. Okay, now how does this help us? This helps us, what is L of x? L of x is basically a linearization. Or in short, linearization of f at x is equal to a. When the value is near a, at a, obviously f of x is equal to the linear function near a. If the value is near a, then this is the linear approximation of this function. Now, remember, there are multiple linear approximation. It depends where you are taking the point. Are we good, guys? You understanding?
Yep.
Now remember, what is this? What is this L of x? L of x is basically it's an approximation to f of x, right? So L of x basically approximates f of x near a, or you can say at x is equal to a. Remember, f of x is some kind of exponential function in this case. So what is L of x now? Linear approximation. Linear approximation, or you can also call it tangent line approximation. Now, we are going to do an example to solve this problem. So I'm going to do 4 examples. Obviously, we only touched on linear approximation. We're going to touch on differentials later on to see errors and stuff. That's what differentials approximates. Now, at the moment, I do have some examples that we're going to solve. So see the first example. Now you basically using this knowledge, you can find the square root of anything, any number. So here's my first example. Estimate the square root of 30 using differentials and linear approximations. Okay. So basically what we're doing is we want to use linear approximations to approximate this. What differential means, like to differentiate. So we set up a function. So we say let f of x be equal to square root of x. Are we good? We say let f of x be equal to square root of x. Now, what is an a value? You need to choose a value close to square root of 30, basically a known perfect square. So what's the closest value square to square root of 30?
So we have 25 and 36.
So which one is the closest?
25.
Right, so we'll choose 25. Good. So we're going to choose the a value to be 25. Right. So because that's the closest, you have to choose the closest to minimize the error margin. You can see the distance here is 5 and the distance away from 30 is 6. So we have to choose 25. Right. So after we choose the function, we need to get a tangent line, a linearization function. Right. Because remember, you don't have a calculator, you're trying to approximate. Okay. So let's try to approximate this. So what we're going to do is we're going to find f prime x, right? When you find the derivative of this, is 1 over 2 root x. Now, how I got that is because this is x to the power half. You're finding d dx of x to the power half. To differentiate x to the power half is half x to the power negative half. X to the power negative half comes down, becomes square root of x. So 1 over 2 root x. Now, what do we do in this? We substitute the value of 25 inside here. So you say f prime 25 because we're finding the slope. Okay. Remember, what's the first thing? We're trying to find the linearization function. What is the linearization function? We just did the formula above. So what's the formula above? The formula above here is this here. So you can see what I'm doing. I'm finding the I'm finding step 1, find the linearization function. That's what I'm doing, right? Okay. So now I'm substituting 25 here. So I'm getting 1 over 2 times 5. So I'm getting 1 out of 10, which is equals to 0.1. Are we good? I substituted 25 inside the derivative function because this is my slope. Remember, f prime a. What is the value of a? 25. Now, after I get that, I also need to compute f of a. What's f of 25? Now, f of 25, you substitute into the original function, which is just basically square root of 25, which is 5. So now I can get a linearization function, which is L of x. What's f of a? What's f of a? F of 25.
Just 5 here. Yes,
Plus
5.
f prime 25 into x minus 25. Now, I need to simplify this. Let's check. F of 25 is 5 plus f prime 25 is 0.1, or you can say 1 out of 10 into x minus 25. If you open up this entire function, you just get 5. Remember, this is 1 out of 10 times 25, so that's 2.5. So 5 minus 2.5. I'm already simplifying this. All right, so let's see, 1 over 10x. So 1 out of 10x minus 2.5. How I'm getting 2.5? Or we can say, yeah, it's fine. Minus 2.5 is fine, it's perfect. Why? Because 5 plus minus 2.5. So that's minus 2.5, right? Remember, 1 out of 10 times negative 25 is 2.5. And 5 minus 2.5 is minus 2.5, okay? So I've got this. Now, how does this linearization function help us? Because currently what you have is you have the square root of x function, right? Now, the square root of x function looks like this. So if you go to functions and figure out, that's the reason why we did those types of topics first. Square root of x function is a radical function. So we can see 30 is somewhere around here, okay? That's the actual value, 30. But we did not take 30. We took a tangent line approximation at 25, right? So you've got a tangent line approximation going something like, obviously this, okay, kind of like, so I need to slope this line. That slope of the line is a bit off.
Zali, where did the +5 go?
Which plus 5? Oh, yeah,
Here.
plus 5 minus 2.5.
Yeah, +5. So I got
And then
1
minus
over
2.
10x plus 2.5.
No, minus 2.5.
How?
I
Yeah,
added the
and then
constants
plus the
together.
5. Plus the 5, mister.
Yeah, you see. Let's do it.
The same thing you just
5. Yeah, I just simplified the whole thing. 0.1x
0.1x
minus
minus
2.5.
2.5.
Yeah.
And then we add the 2.5 to the
Yeah.
yeah.
Oh, so it's plus 2.5. Sorry.
Yeah.
Not minus 2.5. Yeah, I got you. Thanks. Right. So it's 0.1x plus 2.5, not minus 2.5. Okay, thank you for that. All right. Now, this linearization function, what's the point of this? This is an approximation to square root of x. So we know that this is now is an approximation to f of x, right? Now, what is f of x? Note, f of x is square root of x. I want to find the square root of 30. So f of 30 is the square root of 30. Now, the square root of 30 can be approximated using the linearization. That's the whole idea, okay? Now, if you're going to work out what's the actual value of square root of 30, you can check it out using the calculator. Right,
Mr.
so you
Ghazali,
can check it out. Yes.
is the answer 5.5?
Wait, we're coming there. I need to estimate. Okay, so let's see, square root of 30. What's the actual answer? The actual answer is 5.477. 5.477. Let's put this answer there. Yeah, you're right. It is 5. The approximation is 5.5. But you see how close your approximation is and why it is a good tool to use to approximate. So see, the square root of 30 is 5.47722. Now, I wanted to go and find an approximation to square root of 30. So now I can say L of 30 is equal to 0.1 times 30 plus 2.5. So that's 3 plus 2.5, and that's how we got 5.5. Okay, guys. So you can see how close your approximation. The actual answer is 5.477, and the estimated answer. This is a linear approximation answer. Linear approximation. Right, it's an approximation answer. Okay. Now, next thing is to figure out what's the errors. So what's an absolute error? The absolute error is the actual minus the 5.5. So basically the absolute error. So you can say the absolute error is f of x minus the linearization, L of x or L of a. F of a minus is f of not f of a, f of x minus L of x, whatever that value is. Remember, it is at 30. The x value is at 30. So we're taking 5.5. It doesn't matter whether you take that minus that because you're taking the absolute, right? So in this case, it's 5.477 double to 5.477 right? Minus, I'm just taking 6 significant figures, minus 5.5. And check what's the answer there. Minus 5.5. We will get negative, we'll get 0.02277. Let's just take 5 significant figures. Are we good? You guys are understanding there?
Oh, there is absolute here, absolute brackets.
Yeah. So
Positive
the error. Yeah. So basically, the whole idea of showing you this is to say that, yeah, I do have an error in my approximation, and the error is, look at the error, it's so small. It's tiny error. Are we good, guys? Make sense?
Yep.
Yeah,
So,
makes
Mister, we're
sense.
just using a a modified slope-intercept formula.
Yeah, that's it.
Okay.
That's what we are
Okay.
doing.
Based on f of x and f prime, a and f of a, and then x and y, or in this
Yeah,
case, y tangent
tangent
and
line
f of a.
approximation.
Yeah. Okay.
Yeah,
Okay.
that's it. We're substituting 30 in the original function and checking. First, whenever you're estimating anything, you have to identify the type of function that you are estimating. Because it's square root 30 is a radical function. So you have to model this example with a radical function. Make sense, guys?
Yep.
Right, excellent. I just had one more thing to do, just not that. Remember, there are some important stuff that we need to know, not just the absolute error, what's a relative error as well. Like compared to the entire thing, what is a relative error? So what's a relative error? 3 types of errors we got relative error. Relative error is basically this absolute error, right, over the actual. So it's the absolute over the actual value. So what's the absolute error? 0.02277 divided by what's the actual value? 5.47723. So if you try to calculate this, I do have a value here, which is approximately 0.004158, whatever. All right.
Mr.
And
Can
then
I
you
just
also get
put
a
absolute
percentage
error
error.
over f of x?
Yeah.
Because we put f
That's
of
what
x
it
is
is.
equal to square root of, okay.
Yeah.
F
And the
x.
percentage error is taking this and multiplying by 100. So you're taking the relative error and you're multiplying it by 100. Right, so just call this a relative error, RE, multiplied by 100. You will get 0.4%. 0.4158%. So you see it's less than 0.5%. Can you check?
Mm.
So the error in a calculation is less than 0.5%. So that's what it is. Are we good, guys? Make sense?
Yep.
Right, now let's look at the next example. So that's what we're
One
doing. We're
question.
just looking. Yeah.
Sorry, Mr. Ghazali. Why do we need the relative error and percentage error? Can you say it again?
We need the relative error to check what's the deviation away from the actual answer to the estimated answer is very important.
Oh, okay.
You know what the
Right.
relative error defines is basically the reason why we need the absolute error is to check the deviation away from the actual answer. So the deviation away from the actual answer is 0.022. But when you work out a relative error, it's better to work out a percentage error. Relative error is just kind of like a probability. Okay. But the percentage
Oh,
error
yeah.
gives you the how many percent off you are from the actual answer. The actual answer is 5.477, but your percentage error margin is 0.41. So when you're doing like AP statistics and stuff, you can do some hypothesis tests to confirm whether if this is acceptable or not in the real world, depending on the type of data that you have. Are we good, guys?
Yeah, thank you.
All right, excellent. So it's more applied in the real world, in stats. We do these types of stuff to check. There's something called like level of significance and stuff that you work with. Yeah, okay. So the second problem that we're working with is we're going to find a linearization function. I already did a radical. I'm doing another radical now. So at least you know what's a linearization function. It's a linear function, or you can call it a tangent line approximation. Okay. So see, linearization function. We got g of x and a is 0, and use it to approximate 3.96 and 4.17. Determine whether each approximation is an overestimate or an underestimate. Let's check. So first we will start off by finding the derivative. So we got g of x, which is equals to, you find g prime x, which is d dx. Reconvert this function as x plus 4 to the power half. But if you already know the rule, you can just say 1 over 2 root x plus 4. So that's half x plus 4 to the power negative half. And if I differentiate the inside, just 1. So if I simplify this, I get 1 over 2 root x plus 4. Okay, guys, that's what we have as g of x. Now they told us a is equal to 0. So we will find g prime 0. Right, so g prime 0 is 1 over 2 times 2, so quarter. Okay? And what is g of 0? We also need g of 0, which is just 2. What's my linearization function? Is f of x, f of a plus f prime a into x minus a. Now, that's what it is, but now I need to change the function to g. It's not the f function, it's a g function. Right? So what's g of a? G of a is g of 0. A value is 0, right? So it is 2 plus what's g prime 2? Remember, a is equal to 2, sorry, a is equal to 0. So g of 0 is 2, g prime 0 is quarter, and x minus 0. So I have a linearization function which is 2 plus quarter x, okay? Which is approximately equal to f of x, correct? Which is approximately equal to g of x. Near 0. It has to be near 0 because we're substituting a value at 0. Are we good, guys? Make sense?
Wait, Mister, what
Yeah.
do you mean near 0? Are you saying that it cannot be 0?
No. You see, like this one here. When we
Yeah.
substituted, 25,
Oh,
the
we were getting
approximation is near.
as close as possible. Okay.
Yeah. Should it be near 0 or and use it to approximate? No. What I mean is at x at a is equal to
At
0.
A
That's
is
what I
equal to
meant.
0. Yeah,
Yeah.
it can't be near
At
because we
at a
have a
is equal to
value.
0. Yeah. Now, if I try to find L of let's see. We have now a tangent line approximation. We have a linearization function. Okay. Now we want to estimate these things. Approximate square root of 3.96. Okay. Makes sense. We want to approximate the square root of 3.9. So let's look at the original function. Remember, g of x is equal to the square root of x plus, it was x plus 4, right? Makes sense. Isn't that what the function is? The original function is g of x, which is square root of x plus 4. Okay. Now, you want to find the square root of 3.96. How are you going to approximate that? What value of x are you going to put here to get 3.96?
4,
No,
right? Or 0 to approximate, right?
I want to approximate. No, I'm not approximating. If I want to find the actual value, what value of x will you put inside here?
To get something close to 3.96?
No, exactly 3.96.
Oh,
I want to
exactly.
approximate.
Minus
Yes,
0.04.
excellent. Yes. So you need to go and substitute square root. You want to find square root
Okay.
of 3.96. You want to find the square root of 3.96. This implies the x value needs to be negative 0.04.
Yeah.
So basically, if you substitute negative 0.04, you will get square root of 3.96. So if you are substituting negative 0.04 inside g of x, you have to substitute the same in the linearization function as well. So now I need L of negative 0.04. So I need to substitute negative 0.04 inside here. Okay? And negative, so I need to say 2 plus quarter times
Okay.
negative 0.04. So I think you're going to get 2 point, no, not 2 point.
1.96.
Wait. Minus
Oh, sorry.
0.01 because you're taking that and dividing it
Yeah.
by 4, right?
Yep.
So I will get 1.99.
And Mister, this is approximately equal to g of 3.96, right?
Yeah.
No,
So what
sorry,
is,
g of 0 negative 0.04.
yeah. So
Okay.
you can just say square root of 3.96 in this case and check what's the actual value. Wait, let me not take that out. Let's put it here. So we can say g of negative 0.04 is the same thing as saying square root of 3.96. Let's work it out. Square root of 3.96. I'm getting an answer of 1.98999. You see,
1.989.
all so close. 1.98997. 1.98997. Why do we need to take so many decimal places? Because it makes a big difference when you're working in millions, right? So that's the reason why more decimals. When you take more decimal places, you get a much accurate answer. You don't have to round off to 2 and 3, like how we do it at school. Right.
So,
So,
Mr. Ghazali, sorry, one question, please.
mhm,
We right now take approximation, which is 1.99, yeah? And
mhm.
the real answer is 1.98.9899. So how we can find the exactly same answer without calculator?
Yeah,
The
that's what I'm
final
saying.
answer.
If you don't have a calculator, you're going to use 1.99. You get it?
Oh, yeah.
Yeah. The whole idea of approximation techniques is not to use a calculator, right? Because if you have like more complicated functions and stuff, the calculator won't help you. The derivatives will help you. All right, so we got 1.99. Now, next one, 4.17. How will we estimate 4.17? So we do the exact same thing. We say g of x is equal to square root of x plus 4. And
So do
I
you want
want,
like absolute error for both of these, or
no.
absolute and relative? No need?
I
Okay.
don't need the errors because it was just a concept that I touched on, which you
Okay.
already know now. I don't need to work out
Okay.
all that. You can work out the percentage error in these two. It will be very tiny. It'll be like
Yeah.
0.001%
Yeah,
or
it's
something
very
like
low
that.
because I got
Yeah.
2.3 to the negative 5. Extremely small
Yeah,
value.
is very small. So
Okay.
it's negligible in that case. You
Okay.
can see the answers are identical if you go to 2 decimal places and stuff. So now x is
Okay.
equal to 0.17, right? So if I try to find g of 0.17, I'm getting an answer of square root of same thing, square root of 4.17. This case, I'm getting an answer of 2.04205, 206, 2.04206, 2.042. 206. Okay, that's the actual answer. I don't want the actual answer. I want the linearization answer. So in the linearization function, you need to substitute what? Not negative value. You need to substitute this x value, 0.17. Okay. So let's substitute 0.17 in here in the linearization function and see what we get. So 2 plus 0.25 into 0.17. And that's going to give me 2.0425.
Oh, you put A0? Is A0 is same, yeah? A equals
It's
to
almost
0.
the same. See, it's almost the same to 3 decimal places. Look at that. See how accurate the answers are now.
Oh, yeah. I see.
Okay. So now in both cases, are they overestimates or are they underestimates? You see the linearization determine whether each approximation is an overestimate or an underestimate. Isn't the approximations are overestimates? See, the actual answer is 1.98. I'm getting
Yeah, they're both
1.99.
overestimates, Mr.
Yeah, so
They're
this
both
is an
above
over.
like
Yeah,
the
yeah.
amount.
Above the function.
Yep.
Overestimates, right? And this is also an overestimate.
Mm-hmm.
Right, so that's great. Now, next part. Let's see if we have more examples. Right, so this. All right, let's look at the next one. Okay. Next part is a different concept, which is dealing with differentials, right? Differentials is a change between functions. So let's see what is a differential. Just a second. So we want to check the differential. What is dy? Right. So remember when we said dy, when we said f of x is equal to y, we said y equals f of x. Okay. Then we found dy dx. Correct? We found dy dx is equal to f prime x, isn't? We can find dy. So this is the differential. Dy is equal to f prime x and take the dx across. Are we good? This is a differential. Now, graphically, what is a differential? I'm going to explain that. Using a graph, what is a differential? So assume I have some function, any type of function, like that. Right, and I'm going to draw a tangent line. Let me just scope this function a bit. I'm going to draw a tangent to this function. Right, so I drew a tangent line to this function. Let's call this is my f of x function. And that's my tangent. Take 2 points. If I take a point P and take a point Q, okay? Now at point P, call this point X. And at point Q, so point P will be X and f of X. The Y value will be f of X. And point Q, move away from, this is not even vertical. 1 second. Because we're learning what's the differential, right? I'm going to break up the line here, put broken lines. Okay, so I'm taking a distance from X to point Q. I'm taking a horizontal distance. This horizontal distance we call change in X, delta X, okay? It's like a particle. If a particle moves from point P to point Q with the horizontal change in X, what is the vertical change? That's what we're trying to figure out. So this point here now becomes X plus delta X. Are we good, guys? Make sense? So if that point is X plus delta X, what is this point over here now? What's the Y value at this point? Look at the Y value here. The Y value here will be, it's going to be F of X plus delta X.
Mr.
Delta is a
Ghazali, one
triangle.
question.
Yes,
Um,
yes.
Delta x can be negative if, for example, go to the left side.
Yeah, it can. I'm not
It
saying
can,
it's
yeah.
only positive. Yeah, it can be negative. There's no issues. See, like
Mm.
this value here.
Wait, mister, how
Uh,
can distance be negative?
not distance.
Displacement can be, but yeah,
Yeah,
it's
yeah.
technically distance.
No.
Because
He's
it's
talking about can delta X be negative? Yes, it can. I'm
oh
saying
that
delta.
way. Oh
Yeah.
yes, it
If
can be.
you're moving,
Yes.
yeah,
Okay.
theoretically it can, but if you're looking
Theoretically
at
it can.
practical point of view, no, it can't because you're looking at particle moving,
Yeah.
right? Movement of a particle. Okay, now let's draw this triangle over here. Okay, so the distance from here, the horizontal change from P to Q, P to Q, the horizontal change is what? The horizontal change is just delta X, or we call it dx. Dx and delta X will be the same thing. Are we good?
Oh, sorry. The sign of D, it that means that the very small number, no?
Yeah, yeah, yeah. It's minute number, yes. And
Uh,
no, 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 no. In this case, delta x and dx means is a change in x. That's it. We're not talking about making it very tiny. We're not working with the limit here. Okay?
okay.
Yeah. So dx is equal to delta x. And if this is PQ, call this point R, all right? Now, R is important. Wait. Why did I put f of x plus change in x? This is not f of plus change in x. F of plus change in x will be here at R, because now I went and put it onto the tangent line. That's incorrect, not on the tangent line. At this point, because both the points are the same, x and f of x, then I can call this f of x, and it's also on the tangent line. But over here, that's not, it should have been here by R. This is f of x plus delta x. Okay, the change in x. So what is this vertical value? What is this vertical value here? We call this vertical value here from this point to this point, we call that change in y. Now there's a big difference between change in y, the actual change in the function values, and the differential change. So look at the differential change now. The differential change is here from point Q. Let's label this as point A, man. All right, so from A to R, AR is basically delta y. And what is delta y? Delta y is the actual change in y, okay? So what's the actual change in y? F of x plus delta x minus f of x. Are we good? It's a higher value minus the lower value, basically. You understand? A to R. And then what is A to Q? From A to Q, that vertical change is called dy. And that's what a differential is. Make sense? So A to Q over here is the dy value. Wait, let's use a different color. This is basically dy. Okay. A to Q is dy. And that's your diagrammatic representation of what a differential is. So remember, the differential is from the function curve, right? From the points of intersection of the tangent line and the function, right? Tangent line and the function only intersect at one point. That's why it's called the tangent line. From there to the highest point on the tangent line. Are we good, guys?
Yep.
Right.
Wait, but Mister, I thought
Now,
delta y and dy were the same thing,
no,
because
it's
it's
not the
both
same
like
thing.
change in
You see, the change, if you change the value of x horizontally,
yeah.
that is the same. But over here, you're getting two different values. Look
Oh,
at
is it
this.
because one is like the differentiated of
Yeah,
the
one is
original
one is the
function and
differential. Yes,
okay. So
one is
delta
the
y
differential. Delta
okay.
y is the actual change
Is the actual
in the
change.
function. Yeah,
Yeah,
and the differential change is an estimated change.
is an estimate. That's why it's
Because
like
you
that's
see, you
where
got,
the linearization comes, right?
yeah,
Okay.
that's the reason why.
Uh,
Right, so now let's take an example on this. Compare the values of actual change in y and dy for the function. All right, so first we'll find dy, okay? So we're going to solve part A first. So we find f prime x, all right? What is f prime x? 3x squared
3x squared plus 6x.
minus
Oh, sorry,
6x.
minus
Oh,
6x, minus
minus
6x.
6x, yeah.
Yes, so what is dy? dy is f prime x dx. This is a differential, all right?
Is a differential.
We are finding dy first. So
Mhm.
dy is equal to, so where does it move from? From 3 to 3.04. So what is dx?
Oh, it's
D,
3.4 minus 3?
no, yeah. So it's 0.04.
Oh, yeah,
You
0.04.
moved
0.0.
from 3 is
Oh, these are the
0.04,
x
yeah.
values when x changes from.
Yeah.
Okay, okay.
Yeah, exactly.
From
Right.
3 to 3.04. So x to delta x. So now we got 0.04. Now we're going to substitute 0.04 inside this entire function here. So give me the answer. But what's the x value then?
Squared. That's the x value. Oh, no, it can't.
No, dx.
Yeah,
dx
dx is
is
0.04.
0.04. So what's the x value? It starts from where? It starts from
0.2?
3.
And do we find the vertex or something
No, it starts from
of
3.
the
See, so the
differentiated?
x, yeah. So the dx value,
Hmm.
1 second, man. You don't know what to substitute here. You're substituting a value into dx. Yes, that's
Yeah.
good. What about substituting a value into x? You also have to substitute a value into x. What value are you going to substitute into x? We got dx, which is great. What is the x value? The x value is at the point, it's a derivative. So you need to start at 3. So you need to find the x value is 3 because you're moving
Okay.
from 3 to 3.04. So the x value is 3 and the delta x is 0.04. So now you need to substitute 3 inside here into x and dx is 0.04. So let's work that out. So you're going to say that is 3 is
9 times,
27.
it's 9 times 0.04. It will be 0.36, yeah? I think, I believe.
0.04, we're checking now. Yeah,
Yep.
getting 0.36. Good.
Oh, yes. Yeah.
And what is change in y? The change in y will be f, the original function f of 3.04 minus f
Minus
of
3.
3.
Sorry, f of 3.
Yeah, yeah. So work that out. Ah, man, that's such a big story.
Yeah, it will be
Mm,
bigger, yeah.
okay. Look. I have it worked out. You have to substitute some values inside here and there. F of 3.04. I got 28.094464. Don't bother working it out, right? You know what to do.
In the original
0.
function.
Yeah, our original function is f of 3.04. You need to substitute into the cubic.
3. Okay, 920. What am I doing?
28.094464.
Yeah.
And f of 3 gave me uh
9
f
and
of
3.
3 f of 3 gives me 4 only.
4. It just gives you
No,
4.
wait. Sorry. F of 3.04 is not this value here. F of 3.04 is, what is f of 4.36?
4.36. Yeah. Because it can't be such a huge
4.36,
value.
yeah.
4.36 minus
4.36
4.
9664. And f of 3 gave,
4.
what was f of 3? F of 3 gave me 4, yeah.
Yeah.
So you're getting
Oh, okay. This is where the approximation is then.
0.369, yeah,
Okay.
664. So remember what I told you? This is the actual change,
This is the actual
and this
change.
is the differential change.
Linear approximation. Or not
Yeah.
linear, but yeah.
Is this a differential change in y?
Okay.
It's like saying, okay, the particle moved horizontally. Remember, this is, see, if a particle moved from here to there, right? So horizontally, it moved 0.04 units. So
Mhm.
vertically, it moved what? The actual is 0.369664. You see, the differential and the actual is very close to each other. That's the whole idea of linear approximation and differential. You don't want to have a very large difference. Okay, make sense?
So is it that
Yep.
mean that dy is equals to the delta y?
No,
No,
it's approximated to be delta
it's
y.
approximated. Because you said,
Yeah, it's
Mr.
Yeah.
appro-
Delta Y is from the differential to that one point,
no.
right?
I said delta y is the actual change in the function value. This is a
dy,
correct answer.
dy,
Yeah,
dy.
dy is a
Oh, yeah.
differential change.
It's the
dy
differential
is a
change.
differential
Yeah.
from the starting point to
Yeah.
the linearization
To the
point. That's
linearization.
why
Okay.
that's why you're gonna have overestimates and underestimates for that.
Yes.
Yeah, you can have overestimation or under. Okay, I'm not gonna do part B now because you already know what's happening. It's the same thing, same process all over again.
Mm-hmm.
Makes
So
sense.
what do you mean
So
by
we
compare? Compare in
compare
that
the
case the same.
value. Yeah. So basically, we're comparing the values. We're checking. See this value gave us 0.36, and that value gave us 0.36. Yeah, good question. We need to compare. So
Don't we
we need to work
subtract
out.
or like find the difference?
Yeah.
So
We need to find the difference.
0.009664.
Yeah, we're gonna do that now.
So just we
No,
should
we're gonna
find
say
just the difference for them.
no. We're just gonna say dy is approximately equal to change in y. It's
Oh
not a
yeah.
major. Dy is approximately equal to change in y. Okay,
Yeah.
Okay.
so we're just gonna say that. That's what.
Wait, so Mr. Is this also saying that L of
Wait, no. We
X?
can't really wait. We can't really compare here because we never work out the second one. We're supposed to say as delta x delta x gets smaller, dy will become approximately equal to as delta x becomes smaller. Because you're supposed to work out the second one as well. It's fine. You don't need to work it out because you can see even for the second one, you'll get a much better accuracy because this is like 0.37 and that's 0.36. You can check. This is 0.36 and this is 0.37.
Yeah.
So as delta x becomes smaller, this is the general theory. As delta x becomes smaller, dy will be exactly equal to change in y. Because eventually what's going to happen? If you make it smaller and smaller, close to zero, if delta x becomes close to zero, you're going to have a tangent line approximation and f of x to be the same.
So is it mean
Isn't?
that this is our final answer?
Yeah, this is our final answer. I never do part B. You're supposed to investigate part B and check because you see, we are
It's gonna
making
get
this
closer
closer to each
yeah.
other. It's getting so as delta x becomes smaller, dy becomes change in y. The differential becomes the estimated change in y. All right, great. I just have one more example, right? Okay, that's the textbook. I changed it a bit from the textbook, right? So the radius of a sphere is measured to be 7 centimeters, right? With a possible error in measurement of at most 0.03. Are we good? You understanding the problem?
Mm-hmm.
Yep.
Use differentials to estimate the maximum possible error in the calculated volume, right? So
Yep.
what are we modeling here? The volume of a sphere. The volume of a sphere is 4 over 3 pi r cubed. When you maximize the volume, what do? You say dv over dr, isn't?
dr, yeah. dv over
So I'm gonna put
dr
the dr. I'm gonna put the dr on the other side.
on the other side, yeah.
Yeah, so I differentiate this. 4 over 3 times 3 is
4 pi r squared.
4 pi r squared dr. You understood that? Because we're trying
Yes,
to maximize.
exactly.
Next, we are given that the radius is 7
Oh yeah, substitute the numbers. Yeah.
Just
49,
substitute the numbers, and the
48,
error is 0.03.
6.
So dr, the radius is 7 with a possible error in the measurement of at most 0.03. So dr is equal to 0.03. So just substitute the numbers and you see what dV is now. What's the change in volume? Differential change in volume.
Oh, it will be.
Okay, use pi as pi, okay? Please use
196
pi.
times 4. Oh, sorry, 196 pi times 0.03. Because 7 squared is 49 times 4 is 196 pi times 0.03.
And yeah. If you multiply that out, I do have an answer here. I put 5.88 pi. Just keep pi on its
5.88
own,
pi.
right?
Yeah,
cm cubed, okay?
okay.
So what is this? This is the maximum possible error in the volume. But let's just work out what's pi not in terms of pi now, because it does make sense. Let's multiply it by pi. So use pi on the calculator as like how you were doing it. 5.88 times shift pi.
Shift pi
So
is
I'm getting 18.47.
18.4725648. Yeah.
18.747. 18.4725
25648.
648 cm cubed. Okay, so that's the maximum possible error that you can get. Use differentials to estimate the maximum possible error in the calculated volume of the sphere. Okay. If the radius changes by 0.03, that's number one. Okay. What's number two? The relative error in the volume. Yeah, so the relative error.
Don't we have to find without dr, mister?
1 second. The relative error will be equal to, we can just take, because
we
remember
have to find
dV,
4
wait,
pi
1
r
second.
cubed.
1 second. Remember dV is approximated to be a delta V.
Why?
Delta V.
Delta V.
Yeah, we learned that in the previous example. Right. So it's fine. Delta V is a change in Y values, isn't?
Yes.
So we can just say dV over V.
dV over V. Okay.
Right. So what is dV over V? dV is 4 pi r squared dr. 1 second. 4 pi. What is dV? 4 pi. I'm trying to simplify this. 4 pi.
Oh, trying to. Okay. Without the radius.
4 pi r. Yeah. I'm not going to substitute all the values as yet.
Okay.
I'm going to say 4 pi r squared dr.
Yeah.
Over 4 over 3 pi r cubed. Yeah. Let's see what we get here. So we can see the pi's cancel out.
Okay.
The 4's cancel out. So remember that's 1 divided by 1 over 3, which is 3.
3.
The r's cancel out. So dr over r.
dr over r.
Check if you understand that. You understood that?
Yeah, it makes sense. Yep.
Now, what is r? What's dr from the previous example? R was 7.
Yeah, r was 7. dr was 0.03.
Yeah. So let's substitute that inside. So we'll get the relative error like this now.
Okay.
So it's much more easier than substituting the whole thing.
Yeah.
Right?
And then it's like, okay, this 18.47 is with the pi and it's with the 4, so it wouldn't have worked. I got 0.01.
No, it will work. What do you mean? It will work.
Oh, if we plug it in, yeah, if we plug it in that way,
yeah, it will work.
But then we'll have to solve for 4 over 3 pi r cubed.
No, nothing to solve. You already got r and dr. What do you need to solve for? You can substitute it directly inside here. No issues.
Yeah, okay.
So in
There's
this
no
case,
issues. You can just substitute.
Sorry, the absolute one is a 4 pi r squared dr, yeah? The relative error is equal to the absolute
yeah. The dV, the change in the volume is the absolute.
And delta V is actual. Okay.
Yeah.
Okay. It makes sense, yeah.
All right, so what we got here now
I got
is
0.012857.
0.012857. Correct. And the third one, what are they asking us for here?
Percentage,
the percentage error
times
You
100.
just take this
1
and
point.
yeah, just take this and multiply by
Yeah,
100.
same thing. Yeah.
So percentage error is equal to 1.2857%,
Yeah.
which is very small, right?
Mm.
Percentage error is 1.2857%. Yeah, so these are some of the applications in problem solving, right?
Yep.
So how to take any complicated function and make it into a linear function. I can do another example. Example of what is sine of 25 degrees. Sine of 25 degrees. Let's take one more example and we'll end off.
Oh, we approximate, right?
Yeah, so I'm
Yeah,
just doing
sine
an
difference.
additional example. Yeah, so
Yeah.
because now you're going to use trig derivatives here. What
Mhm.
is sine? Estimate the value of sine 25 degrees. We know what is sine of 30. It is
It's
half.
approximately half. Yeah.
Yeah,
1 over
But
2.
now, but now first you need to convert the 25 degrees into radians.
Multiply P or multiply 180 over pi.
No, the other way. Pi over 180.
Pi over 180.
Pi over
Yeah.
180. Sorry.
40
Yeah, so
over
theta
360.
equals
1 over 9. Pi over 9. No.
One second. 25 times. Wait. Why don't we take something that we have already worked with before? Instead of taking sine 25, why don't we just take sine of 15 degrees? Because we can use sum of angles to solve this, isn't it?
Yeah.
Oh,
Yeah.
45
yeah.
minus 30.
30.
Let's take
Yeah.
sine 15 and see if we actually get an estimated answer using differentials, all right?
Okay.
So we can say, let's estimate this now, right? So we
So
can say,
first, are
okay,
we
this
gonna
is
do
pi by
sine
12.
sum? Or sorry, sine difference?
Yeah,
Or are we gonna
no.
approximate
We're going to
first?
use linear approximation. We're going to use
Okay.
linear approximation.
Okay.
So we say let f of x be equal to sine x.
Hmm.
Okay, and the a value is a
Where
very
x
good
equals a.
question. What a value are going to use now? Because if you're going to use 0 and 30, both of them are is like in the middle. So I think 25 was much better. Let's keep it as 25.
Yeah, let's keep it 25.
So we're going to choose a value
A
as 30
at,
degrees, but we can't work in degrees, huh?
and we'll change it to radians, so pi over 6.
Yeah, we have to. So let me change this now. 25 times
I got 5 over
times
5 pi over
shift
36.
over 180, 5 pi over 36. Yeah. So sine of 5 pi over 36. Okay, that's what I'm trying to estimate. But now the closest value is 30 degrees here, isn't?
Yeah.
Closest to 25 is 30 degrees. That's a special angle. So that's pi by 6. So I should get an answer which is very close to half. Correct?
Yep.
0.5. Now let's see. So let's find the linear approximation of sine 25 or sine 5 pi by 36. So you're going to say f of x, f prime x is equal to cos x.
Cos x.
Are we good?
Yeah.
Right.
Yeah,
So now we're going to substitute. Now we're going to substitute f prime pi by 6.
Is equal to root 3 over 2.
Cos of 30. Root 3 over
Cos of
2.
30, root 3 over 2.
Root 3 over 2. And what is f of pi by 6? We also
Half.
need f of pi by half. Right. What's the linearization function? L of x equals f of a plus f prime
F
a
prime. X
into
minus
x minus a. Yeah, so now we're finding L of
Mister, this is where x equals x isn't a, right? X is a different variable in this case.
x is your 25
X is your
degrees, the original
25.
function.
Okay.
Yeah,
Okay.
yeah. Not 25 now because that was degrees. We are working in radians.
5 pi over 36.
Yeah.
Okay.
So what's f of a? F of a is half plus root 3 over 2
x minus
x minus pi by 6.
pi by 6.
So now we're going to find L, so which is approximately equal to this here is an approximation to f of x. Right, so now what are we finding? F of x is equal to sine x. we are finding f of 5 pi
over 36.
by 36, which is sine of 5 pi by 36, which is the same thing as saying sine of 25 degrees if you put your calculator in degree mode. But now we are finding this. We can't substitute. So what is your x value? That's your x value. So
Okay,
your x
and we
value,
plug that
L,
in. Okay.
yeah, L of 5 pi by 36. That's what we want. Is half plus root 3 over 2 into 5 pi by 36 minus
pi over 36. Sorry, pi over
6,
6.
6,
6 pi over
6 pi.
36.
Yeah, I changed
Okay.
it to the same denominator. So now you're going to have negative pi by 36.
Yeah.
It's multiplied here, right? Okay, so now we're getting something ugly here. Just do it on the calculator. Multiply it out.
Okay.
I think it's very minute. It's very close to 0.5.
Yeah, it is. Root 3 over 2 minus pi over 36.
This 0.40 something or
0.4948 or something. Check.
0.424.
Ah, 424.
424.
Yeah.
424.
You can check, mister. I don't know.
Yeah.
But it
and
seems.
I want what is okay, 424. Okay, that's fine.
And then
And what is sine of 20?
You're saying? Sine
Yeah,
of
I'm gonna
20.
change my calculator to degree mode, and I'm just gonna put sine 25.
0.4226.
Yep, very close.
Wow. Yeah.
So this is 0.4226. That's the power of linear approximation and differential.
Yes.
It kind of like squeezes the answer very close to your actual answer. You won't find very big percentage deviations. Okay, now let me end off the session, then I'll take some questions.